Hello, in this lesson, we're going to be back to the topics about absolute max, absolute min, local max, and local min. So first of all, we want to talk about, because this time we are going to use derivatives as a tool to find local max, local min, absolute max, and absolute min. And even though in the definition of local max, local min, absolute max, absolute min, it does not include, it does not require continuity nor differentiability. Okay, so first of all, we like to learn what is the first order derivative tell about the function itself. And so here we have an increasing, decreasing test. Okay, and here's the statement. So increasing, decreasing test. And this can be treated as a theorem. Basically, what it says has two items. First, it says if a derivative, first order derivative, is greater than 0 on an interval. On an interval. Okay. It could be a, b, or whatever interval. Okay. Then, but it's not on single number. Okay. On the interval, then f is increasing. Then f is increasing on the interval. Okay, so from the sign of first order derivative, we can tell if a function is increasing or decreasing. And the second item is, of course, if the first order derivative is less than 0. So basically, I'm going to copy every word and just change some word. Okay, so if the first order derivative is less than 0, then the function is decreasing on the interval. So it's pretty straightforward. It's pretty straightforward. So now we're going to prove this result. We're going to prove this result. Before we prove this result, okay, we like to review the definition of increasing function. Okay, so the definition of increasing function. The definition of increasing function is f of x, f of x, f of x1, okay, x1 is input, x2 is input. Okay, so f of x1 is less than f of x2 whenever x1 is less than x2. X sub 1 is less than x sub 2. Okay, so this is the definition we have learned before. And of course, the definition of decreasing function would be that f of x1 is greater than f of x2. So it's reversed. So let's see how we're going to prove this theorem. We prove this theorem using intermediate value theorem. Okay, we're going to use intermediate value theorem. So we're going to prove the first case, A. Okay, prove A. Okay, we assume that the function is, the derivative of the function is positive on an interval. Okay? And we choose 2 points. We choose 2 points arbitrarily. Okay, so these 2 numbers are, and choose arbitrarily x1 and x2. And of course, we can arrange them in order. So make x sub 1 is less than x sub 2. So this is chosen arbitrarily from that interval, from an interval. All right. Now, because the derivative exists, right? This obviously tells us derivative exists. And you know, if it's differentiable, it is continuous. So we can say f is continuous on the closed interval x1, x2. All right. It's continuous on this interval and differentiable. And f is certainly differentiable in the open interval, which is a x1, x2. So we basically created a interval, right? On this interval, we can apply mean value theorem. Okay, so both conditions are satisfied on this interval. So by mean value theorem, okay, there exists a number C that's going to be inside this interval, the open one, such that okay, we're going to write the conclusion of mean value theorem minus, that's B is x2, right? And x sub 1, that's A. All right. X sub 2, that's B minus, you mean like if you don't remember that that theorem, mean value theorem, please look at your index card, okay? And that's derivative of at C there. And that means that, you know, because the derivative function at C is it's one of those values, the derivative function on that interval. So this is a positive, right? X2 minus X1 is also positive. Therefore, we multiply both sides by the denominator, X2 minus X1. So that's going to be equal to this piece multiply the denominator. And the parentheses is positive, this is a positive, so the whole thing is a positive times positive. Therefore, f of x2 is larger than 0. And that means f of x2 is larger than f of x1. Okay, so this is greater than f of x2. So it's fitting to the definition whenever x1 is less than x2, f of x2 is larger than f of x1. So it's fitting for this definition. And therefore, since we have chosen x1, x2 arbitrarily, so that is to say f is increasing. on the interval. Okay, for decreasing, the proof is similar. The proof is similar. So let's see on B, okay, on B. So if the derivative is negative, almost everything can be copied, but we're with some minor changes. I'm gonna get this done quickly, okay? So for the case of B, the derivative is less than 0. We also choose x1 less than x2, and f is continuous, differentiable by mean value theorem. There exists C such that, but this time is going to be less than 0, So in this multiplication, we're going to have f of x1 minus f of x2 subtract f of x1. This piece is negative, but this piece is positive. And negative times positive is going to be negative. And as a result, this is negative, and f of x2 is less than f of x1. Therefore, f of x is decreasing. So this is the increasing, decreasing test. Very, very important and very, very useful. And then we're going to talk about first derivative test. Okay, so in this lesson, we mainly talk about the series. And in other lessons, we're going to talk about how to use them. Okay, so next we're going to introduce first derivative test. First derivative test for local max, local min. Okay, we're going to be using the increasing test, decreasing test. So this is what is being stated. Okay, first derivative test. Suppose that C is a critical number. Okay, so in this process, we still need to find a critical number. Is a critical number. Okay, C is a critical number of a continuous function, f. Okay, this function is f. And there's three cases. A, if the first order derivative changes from positive to negative at C, then f has a local maximum. The changes we mean usually from left to right. Okay, so if f changes from positive to negative, okay, positive to negative, negative, okay. The first order derivative changes from positive to negative. Okay, I will show you some cases, okay. Changes from positive to negative at C. Okay, then f has a local, maximum. Then f has a local maximum at C. Okay, so first order derivatives changes from positive to negative, which is from left to right. So let me bring you a picture. So here's the picture. So here's the picture. In this picture, you can see on the left of the critical number. So this is the critical number. We know that the critical number is where the first order derivative equals to 0 or it is undefined, right? Then to the left of C, this is a positive because you can see the blue curve goes up, increases. Okay, so change from positive to negative. Past C, the first order derivative is negative. That's what we mean by changes from positive to negative. Then F has a little bump, right? This is a local maximum at C. And the second case B, it would be changing from negative to positive. Okay, so I'm going to just basically copy this and make some changes from negative to positive at C. Then F has a local minimum at C. So here we have a picture for you. Okay, changes from negative to positive. In this picture, you can see the derivative to the left of C is negative because the blue curve is decreasing. Decreasing derivative will be negative. To the right of C, increasing. So decreasing, increasing. So there's a lowest point. That's the local minimum. C. What if there's no changes, right? What if we have a case like from positive to positive and from negative to negative? So in those cases, no maximum nor minimum. Okay, so we're gonna type that statement. If F prime is positive to the left and right of C or negative to the left and right of C, then there's no local maximum or local minimum, or there's no change, right? So if F prime is positive to the left and right of C. Okay, or another case would be negative, right? Or negative to the left and the right of C. Same, no change. Then F has no maximum. F has no local max nor local min. Okay. So this is the statement. The two cases here, you're going to see that in the neighborhood of C, well, C is still a critical number. C is still a critical number. You can see the tangent line is flat, right? The derivative is 0. But it's increasing here, it's still increasing after. That's not maximum nor minimum. We mean local maximum nor local minimum. Or decreasing and then still decreasing. So negative, negative. So in the third case, there's no local max, local min. Okay, so that's about the second order derivative. How about so that's the first order derivative. Let's talk about what about second order derivative, right? Second order derivative. What does second order derivative say about F? All right, so the next title would be, what does second order derivative say about f? About f. Okay, and the word we're going to use is called concavity. Concavity. So we're going to introduce a new terminology, which is called concave up or concave down. Concave up or concave down. Okay, so I'm going to type the meaning and then we're going to explain to you. Now, if the graph of a function f okay, lies above all of its tangents on an interval, all of its tangents on an interval I. Okay, I'm going to use a different color to represent the interval I. It is called concave upwards. Concave upwards. Then f is called concave upwards. F is called concave upwards on I. A typical example would be our familiar function, okay? Example right here, y equals to x squared. Y equals to x squared. This function, we are very familiar with this function. We're very familiar with this function, right? We have, we're going to graph it. It's a parabola, okay? We're going to draw some tangent lines, right? At different points, we're going to draw tangents. Let me make a little adjustment to the picture. Maybe 12. All right, so this is the curve. We're going to draw some tangent lines, right? So we have tangents. The tangent here, tangent here, right? Tangents and tangents. You can see all of these tangents. There will be more, many tangents. All of these tangents is beneath the curve, and the curve is above all of the tangents, right? If the graph of f lies above all of its tangent on an interval, it doesn't have to be the whole of the curve, it's part of the curve that will make it called a concave up. So this parabola is also called a concave up. However, if we look at another example, okay, and you certainly will get concave down, right? So another example would be concave down. If I just put a negative sign in front of it. So this is just to explain what is a concave up, what is a concave down. I'm going to explain with a negative 12 to 2. You can see in this case, right, all the tangent will be above the curve, and this will be concave down. So this is a concave up, and this is a concave down. So what's the definition of concave down? Oh, sorry, not the wrong spelling, concave down. So this is a concave up, right? So let's write down concave down. Okay, so if the graph is lies beneath or below all of its tangents on I, then it is called a concave downwards. On the interval. Okay, so that's the definition. So what is then, just like increasing, decreasing, we have tests. Well, we also have concavity test. Concavity test. What is a concavity test? Okay, so concavity test. Concavity test. If the first order derivative is positive, if the second order derivative is positive on an interval, then it's a concave up. Okay. If second order derivative of 2 prime is positive on an interval I, I'm going to make that red, on an interval I, then the graph of f, is concave up, upward on I. Okay, let me clean up that drawing from Zoom. Okay. And similarly, okay, it will be concave down. You guessed it. If the second order derivative is less than 0 on an interval, then the graph of f will be called concave downward. Concave downward on that interval. Then you say, what if it equals to 0? Right? What if the second order derivative equals to 0? For second order derivative, positive is concave upward, negative is concave downward. Then how about concave, the second order derivative equals to 0? That's a good question. We're going to answer that question, okay? Before we answer that question, we're going to introduce something called inflection point. Inflection point. Okay? An inflection point, a point P on a curve. It has to be on the curve. Y equals to f of x. Y equals to f of x. Okay. I'm just checking if I'm recording. I'll hate it if I forget. Also, I forgot to kill the recording. A point P is on the curve is called an inflection point. It's called an inflection point. If, okay, f is continuous, first of all, f has to be continuous. If f is continuous there, and the curve changes from concave upward to concave downward, upward to concave downward. Downward. It has to be change of concavity, okay? That's very important. It's called inflection point. It's either changes from concave upward to concave downward, or from concave downward to concave upward. So there has to be a change of concavity at this point, at P. This is very important. And then we're going to answer the question, what if the second order derivative is equal to 0? What if the second order derivative is equals to 0? Okay. The second order derivative equals to 0, those points, whatever points make the second order derivative equals to 0, those points are the candidates for inflection points, because you can see your second order derivative is continuous, and it is continuous, right? From concave upward to concave downward, that will be the sign change from the second order derivative. In the most ideal world, that all these derivatives exist, right? So that's upward is positive, downward is negative. So changing from positive to negative or negative to positive. So it will pass 0. So, however, just like critical numbers are candidates for local max, local min. Second order derivative equal to 0, those numbers are candidates for inflection points. All right, so I would put this down as a statement. So that's to answer the question, if second order derivative equals to, say, d equals to 0, okay? And d is d, okay? I would say d, f of d well, inflection point is the point, right? Is a candidate of an inflection point. So we have to check whether there is change of concavity to determine whether it is an inflection point. If you're going to use second order derivative as the way to find inflection points. Okay, we're going to see this in our future examples. Before we go on, let's look at another test for local max, local min, and we call it second derivative test. Second derivative test. Second derivative test is much shorter than the first derivative test. Okay, second derivative test. First, we're going to suppose the second order derivative exists. Okay, so f double prime is continuous near C. Is continuous near C, near the critical number. Okay, C is a critical number. So suppose, all right, we have two items. Two conditions must be satisfied. First, the first order derivative at C is 0. Well, that just means that it's, it is a critical number. And second order derivative at C, second order derivative at C, just plugging in the C is a positive. Then, right, there are two conditions. Critical number, concave up, right? Then F has a local minimum at C. F has a local minimum at C. You can imagine the situation, right? You can imagine the situation. It's concave up, right? We can almost use the example we did over here. Okay, we can almost use the example we used over here. 0 is a critical number in this case. Of course, it's just a very special case, right? And it's concave up. It's concave up. So this is a local minimum. And B, we will have everything the same except second order derivative at C is less than 0. Less than 0. In this case, we have local maximum. We have local maximum at C. So that will be the second case. Okay. So by this time, we have covered all the concepts. We have covered all the concepts that's related to the study of curves and to study about local max, local min, and possibly absolute max, absolute min, inflection points. And so then follow these, after you study these, look at these examples with these concepts in your mind, and hopefully you put them on the index card when you're working on these concepts with concrete examples. So without further ado, I'm not going to make this too long, and thank you for watching.